Good morning, everybody. I will start by thanking all the speakers for accepting this invitation to share with us some application with PDEs. This section is organized by me and my colleague João Cardoso, both from Coimbra Institute of Engineering. And since I will give also a talk, I asked to João to do the sharing of the section. Okay, João?
Okay. Thank you again for all the speakers and for accepting the invitation. So the first speaker is Hugo Peña Gomez. He is a member of CMUC, Center for Mathematics of University of Coimbra. And he's talking about finite difference analysis and numerical simulation of a light-triggered drug delivery model. Hugo, it's your time.
Thank you. Thank you, all of you, for joining this talk. And first, I want to let you know that Professor Augusto Ferreira and Professor Luis Pinto are my advisors. I am currently a PhD student at the Math department in the University of Coimbra. And this talk is part of a paper that we recently made. Okay. I'm going to start with the summary of the talk. First, the motivation and some key concepts. After that, I will show you the model, some finite difference analysis and the discrete model, a couple of results on stability and convergence, one numerical example, and conclusions and future work. Okay, let's start with the motivation. Well, as you can imagine, it comes from drug delivery and a particular set of techniques that, of new techniques that use some nanostructures. We can think about these nanostructures as tiny spheres containing the drug. And well, these spheres, these small spheres are trapped in a polymeric network, a hydrogel, as they call it in English. And well, this hydrogel is a smart material because, well, it has a high percentage of water, similar to body tissue. Okay, and that's why it's biocompatible with the body. And also, this hydrogel can respond to some stimuli, some external stimuli. So this material can be introduced into the body, into the part of the body who needs the treatment. Yes, and after that, an external stimuli is applied, so the drug can be released. Okay, so there is this area is a promising area of research right now. For example, in cancer treatment. Well, there are conventional techniques and these new techniques I am talking about. Well, this I already said about the external stimuli that can be applied. And some advantages of these new techniques are, for example, that the drug administration is locally into the body. So this allows to reduce the side effects. In some research, they report almost zero side effects. After that, well, these are not invasive techniques. And also they allow the control of the drug over space and time. Okay. About light, I need to say a couple of things. First, how light works as an external stimuli. Well, what actually happened is that, well, you know that light is composed by photons, and the heat of these photons into the chemical compound can actually break the chemical compound. Okay, this is well known as photolysis. And yes, another thing that I need to say is how to model light. Well, because it is an electromagnetic wave, we know that we can model light with the very famous radioactive transfer equation. However, this equation is not easy. It's not easy to solve numerically also. So there are some alternatives to this equation that we can use. For the purpose of this talk, we are going to use Beer-Lumber law, which is possible to use because of the properties of the medium we are considering here. Here you can see a picture, a cartoon, let's say, of the technique. You can see the polymeric network, the hydrogel, containing some tiny spheres trapped into the network. And after applying one of these external stimuli, the drug gets released. Of course, this is a gradual process over the time. So there will be still, after a moment, there will be some drug that is free and it's free to diffuse into the medium. There will be some drug that is still trapped into the network. Now we can jump to the model. The first equation is Beer-Lumber law. I sub 0 is the intensity of the source, okay, the light intensity that arrives to the boundary of the medium. And beta is the attenuation coefficient. Okay, we proposed a diffusion coefficient for the free drug concentration, the second equation. As you can see, here is the diffusion term with the diffusion coefficient D, and also a reaction term, which is proportional to the light intensity that is applied to the bound drug concentration. Okay, and the last equation is for the bound drug concentration. And well, you can see here also the same reaction term with opposite sign. Okay. Well, we complete this model with this boundary and initial conditions. At the time 0, you can see that there is a distribution of bound drug concentration over the domain. There is no free drug concentration at the time 0 in all the domain. And well, we assume Dirichlet boundary conditions for the free drug concentration. Okay. We can write the last system in this form. It's a bit more general because here we named the reaction term of the equation of the free drug concentration as F, the reaction term here as S. And well, you can notice also that we allow the diffusion coefficient to depend on the free drug concentration. Okay. Well, I need to say some things about the finite difference formulation very quick. Of course, we need to use a discrete domain, omega h. Yes, we need to define WH as the space of grid functions in omega h, WH0, the subspace of WH as the grid functions null on the boundary. And well, similarly, WH hat, the space of grid functions in omega h. Well, in omega h0, we define this inner product, and we are going to work with this. And well, some usual finite difference operator, the average operator that we are going to use for defining our discrete model that we can see in the next slide here. Okay, so we defined our numerical solutions as the functions, the discrete functions satisfying this this system. Okay, here we are considering the time as continuous. This is part of the work, as I said, part of the work that we did in a paper. Also, we did a similar work with considering the discrete time. Okay, but here I'm going to present just the part with the continuous time. Okay, maybe we can jump now to the results. We need to establish these conditions for the results. The first one, as you can see, we are asking the diffusion coefficient to be bounded from below by a positive constant. We ask also the diffusion coefficient, the function f and s to be Lipschitz, and a couple of more conditions, 1 over f, that we can bound the function f at any point x and y by a constant time, the second entry, and similar to the function S. So, I want to show you this couple of results. This is on stability, very quick. We don't go in many details because the time is really short. So stability, as you know, means that if we take two solutions of the system that start, let's say, close enough, they will remain close enough in the domain, okay? So this is what we want to show here. As you can see, WF is the difference between two solutions of the first equation, the free draw concentration, and WB is the difference between two solutions also, okay? And we can bound the norm of WF and WB with these inequalities. Here, the result depends, of course, in the form that has this function gamma, which also depends on this norm, infinity norm of this quantity here. But it's possible to show that also this quantity is uniformly bounded, so we get our stability result. Yes. Next, this is a theorem about convergence. Okay. Similarly to the previous result, we need to define the error, which is the restriction of the continuous solution of the system minus the approximation. Okay. This for the first equation, for the second equation similarly, and we can obtain an inequality of this form. Okay, because we ask this h is just the step in space. Okay, and we ask this h going to 0. Then from here we can show the convergence of the method. Okay, now we jump to an example. This is a numerical example taken from. I really want to say that this. There is a paper that reports some data from a numerical, from a laboratory experiment. Okay, so we want to prove. We want to see what happened with our model, if it can reproduce the solution of the things similarly to the numerical experiment, okay? To the laboratory experiment, I'm sorry. So this is only the system of equations that we are proposing. Here we just modify a bit the boundary conditions. Okay, we impose no flux boundary conditions, and well, as said before, this is the free draw concentration at the time 0 is going to be 0. This is the distribution of the bound draw concentration. It's going to be 1 for x less or equal than 0.25, and it's going to be 0 in the rest of the domain. And well, we are going to see here only the qualitative behavior. So we are going to report normalized release rates of the free draw concentration. Well, here is a picture, a cartoon, let's say, of the experiment. Here you can see the hydrogel from 0 to 0.25. And after that, the rest of the domain. And well, this is some results that we had. Okay, we are seeing here on the left free draw concentration against the domain for different parameters, for different values of the parameters I sub 0, which is the intensity of the source. Okay, and as we can expect from the physics of the experiment, the higher that the intensity source is, well, the higher of free draw concentration we are going to have. Okay. And on the right, you can see, well, the free draw concentration release rate against time, also increasing depending on this parameter I sub 0. well, these are the values for the other parameters that we are using here. And next here, we can see the CF release rate, okay? And we are going to see also the relative change for each value of the parameter I sub 0, okay? So this is the most important, let's say, of the most important table of this experiment, of this numerical experiment, because we can see this percentage, the difference between the experimental result and our numerical solution or numerical data. And as you can see, for the parameter I sub 0 equal to 10, we have
Hugo, 2 minutes to finish, please.
Yes.
Okay, please.
We are almost there. Okay, thanks. Okay, I was saying that for the parameter I sub 0, there is a slightly big difference, but as you can see, for the parameter I sub 0 equal to 15, it's more accurate, the method. Okay, so we go to the conclusions, and here I want just to say that, well, we got supraconvergence error bound, a discrete H norm as a result, okay? Also in this work we did, we found similar results for stability and convergence in space and in time and space fully discrete with an IMEX scheme, implicit, explicit, okay? And well, these comparisons with the laboratory experiments suggest that the model is reliable and can provide some useful guidance to optimize light-triggered drug delivery systems. Of course, there are some improvements that can be introduced into the model. And as a future work, we have to study the 2D case with a similar model. Some changes should be introduced because we cannot use Beer-Lumber law for the 2D case. And well, considered also a different scenario where the bound breaks are originated by temperature. And yes, this is part of the references that I use. Thank you for your attention.
Oh, thank you, Hugo. We have 2 minutes. I would ask the participants if there is any question, a quick question to ask to Hugo. I don't know.
I have one.
Okay, Pascual.
In the beginning, the intensity, depending on time or not, you can share with us the mathematical model, please?
I'm trying to move. Okay, I'm going this way. Here,
I depend on x and t on the second equation or only by x. We have I on x.
Yes. I wrote here the dependence in time also, but no. We are considering.
In fact, that does not depending on time.
Actually, it does not. Yes.
Okay. You only depend on x. Okay. Because on the analysis is quite different, but okay.
Yes, it was my mistake to put the time dependence.
Okay, so we have a few seconds to start the next talk. So the next speaker, okay, maybe Hugo, you have to stop the sharing, please.
Yes, trying to
And
do
then
that. Okay.
Yeah, and then I would ask Carla to share the slides. Okay. Carla is a PhD student supervised by Ercilia Souza, and she is a member of Center for Mathematics of the University of Coimbra. Carla is talking about fractional splines in subdiffusion. Carla, go.
Thank you very much. Yes, I'm in a PhD student and I'm in the last year of my PhD. And as John said, my supervisor is Professor Ercilia Souza. First of all, I'm going to talk about classical diffusion. Here, U is the probability of an object to be found at position X at time t, and D is the diffusion coefficient. It was Einstein that in 1905 derived the diffusion equation while working about Brownian motion. Here we have that the second moment grows linearly in time, and anomalous diffusion takes place when some of the hypotheses for the classical diffusion don't hold. In this case, if we have that the second moment grows according to a power of t instead of when the power is not 1, we have anomalous diffusion. If gamma here, the power of t, is less than 1, we are in the presence of subdiffusion that can be seen as the spread of the particles as a slower process comparing to the classical diffusion. If gamma is greater than 1, we are in the presence of superdiffusion and is the faster spreading of the particles. There is another superdiffusion process that is when this moment diverges, the second moment diverges, and then we are in the presence of Levy flights. Here I'm going to talk about only subdiffusion. These are some examples of phenomena that present subdiffusive behavior. And these are some articles where they explain this type of behavior and model these phenomena. So we can have heterogeneous systems with porous medium and variable permeability. In hydrology, we can have the transport of pollutants and contaminants in groundwater. In biology, an example would be the fluctuating proteins and its movement. In electric fields, I have here an old and classic example that is related with printers and how they rely on the transport of electrons. And in economy we can observe the dynamic of financial data. These are just some examples where the subdiffusive model is a good model. I'm going to talk about the fractional differential equation. As I said before, here the second moment grows according to a power of t that is less than 1. And in our work, we use the Riemann-Liouville fractional derivative operator in time whose expression is given by this. So we want to derive numerical methods for this equation, where G is the source term, D is the diffusion coefficient, and as for classical diffusion, sometimes it's difficult or even impossible to get the exact solution of these type of problems. But in fractional differential equations, there are some other challenges, as the non-locality of the operator and the singular kernel of the operator. Because of the operator to be non-local, these type of numerical methods are more complex than for classical diffusion equations or classical differential equations. Because when you are discretizing the equation in time, at each time step, we have to take into account all the information that is before. So this is a lot more complex. There are a few numerical methods for this type of equation, and we wanted to derive one that use fractional splines and maybe relate the order of the spline with the order of the derivative. So, as I showed you before, this is our fractional operator, and we have here an integral. Here is presented the non-locality of the integral, and here is the singular kernel. And we want to deal with this integral using splines. So splines are a combination of piecewise polynomials of a certain degree. There is a well-known spline that is the linear spline that can be described as I have here. And if we consider a mesh, we have these that are the B-splines, and each function is of degree 1. And we can see that the values in the nodes, at the nodes, are 1 if x is equal to xk and 0 otherwise. And as the splines are interpolator functions, to describe or to get the coefficients that we want, we just have to impose that the values of s in xy are equal to the values of u in xy that are the points of the mesh, and we get this formula for the linear spline. But what if we don't have here polynomials of degree 1, but of fractional degree? Then we have this formula for the splines, and these are the B-splines, fractional B-splines. In this picture, I represented the fractional B-splines in color, and the thicker black line are the classical B-splines. We have here the same condition that the spline has to be interpolator, and this type of functions were used in before in wavelets, signal, and image processing. Now we are going to use them to approximate that integral operator. So to discover these CK constants, these coefficients, we use the feature that the spline is interpolator. So this is the value. At left, we have the value of the spline in Ti, and at right, you have the value of the function that we want to approximate in Ti. And if we consider a uniform mesh, then Ti is given by I times delta T. So Ti minus Tk over delta T is equal to I minus K. And if we do that change, we can see the following. This plus means that this has only value when what's inside the parentheses is positive. It's what I have here. This is equal to this if I minus k minus j plus beta plus 1 over 2 is greater than 0. What this means is that j has to be less than I minus k plus beta plus 1 over 2. But as beta is between 0 and 1, we arrive to j has to be less or equal than I minus k. So we can drop the plus infinity in this sum and replace it by I minus k, and then we have a finite sum. So if we consider these to be these coefficients A, to discover the values of C, we have to solve this system. And A here is a matrix that is a lower triangular matrix, and it's a Toeplitz matrix. So we know that its inverse will be a lower triangular matrix and a Toeplitz matrix as well. So we can write the coefficient Ck at the expenses of the values of the inverse and the values of the function u at the nodes of the mesh. Then this is to approximate u by a spline. And now we are going to substitute or replace u by the value of spline inside the integral. That was really all that I did here. So instead of having u, I put it here, the formula of the spline. And as I, using same technique than before, as here C is between T0 and Tn, we can drop this plus infinity and replace it by n minus k. And then we have a finite sum, and we can exchange the integral with the sum. Then our approximation can, it's not yet the approximation, but can be seen like this. And LJK includes this integral that has just two polynomials, and it can be computed by a formula. We just have to take close attention in B and 0 because it's a more delicate case, and we use an approximation to compute this integral. Then we can have the spline, the integral approximation, as you can see here, and do a rearrange of the terms. We can write it like this at the expenses of the values of u. Then we created a numerical method for this equation, this fractional differential equation. When we use the fractional spline to approximate the integral operator, we use the second order central finite differences to approximate the second derivative in space, and we use Craig-Nicolson to approximate the first derivative in time. We computed the error bounds and we write to accuracy of beta plus 1 for solutions that are regular enough. For solutions of this type, like fx times t powered to gamma, the results we got were the minimum of beta plus 1 and gamma plus alpha. And for solutions with less regularity, we concluded that for larger meshes, beta equals to alpha presented smaller errors. Now I have a convergence rate illustration. We chose the source term and the initial conditions in order to have this function as our solution. And we expected to an order of accuracy of delta t over beta plus 1, or another of accuracy of beta plus 1. So here I have two figures where there is the error plotted in a log-log axis. And here at the left, I have the results for alpha equals to 0.2. And at the right side, I have the results for alpha equals to 0.8. In the blue lines, I have the results for beta equals to 0.2 in both of them. In red, I have the results for beta equals to 0.4 and so on until beta equal to 1. As we can see, as the minimum of beta plus 1 and 2 plus 2 alpha is beta plus 1, we got the results that we expected. Here is 1.2 and here is 2, and the medium are all accurate. In the case of a function that is less regular, is C1 in time, we expected a minimum of beta plus 1 and 1 plus 2 alpha. So in the left side, we have alpha equals to 0.2. So the minimum would be beta plus 1 in between beta plus 1 and 1.4. So we would expect an order of accuracy of 1.2 for beta equals to 0.2 and 1.4 for the other betas. As we can see, we got 1.2 for beta equals to 0.2. And for the other betas, we got the 1.3 that was pretty close of what we expected. And if we refine the match even more, we would get the 1.4. For alpha equals to 0.8, the minimum between these two values would be beta plus 1, and we got the expected accuracy results. As a convergence of a numerical method is only completed when we evaluate both the accuracy and the stability of the method, I'm presenting here our results for the stability of the method. So for our splines, we order between 0 and 1. For our case of diffusion.
2 minutes, Carol.
Okay, okay. I'm almost finished. For our splines, if alpha is such that this constant is negative, this constant is given by some coefficients that I showed you before, then the beta method is a conditional von Neumann stable. If alpha is such that that same coefficient is positive, we got a conditional stable method. So we got a stable method with accuracy of beta plus 1, so we got a method that is convergent with accuracy of beta plus 1. This is according to other articles that were already published about a linear spline that showed that their method was convergent or was second order convergent. So our research is based in applying splines in to approximate fractional differential equations. I talked to you about this first article that we published. It was using fractional splines in subdiffusion. We also worked in using linear splines in superdiffusion problems, but now with alpha between 0 and 1. And we consider as well boundary conditions in superdiffusion problems. As ongoing work, we are working with fractional splines, but now with order between 1 and 2, they are a little bit more delicate and require extra conditions. And my investigation is funded by FCT through my scholarships. Thank you very much.
Thank you, Carla. Thank you very much. I would ask if there is any question in the audience. Any question to Carla? The participants can use the question and answers and the chat. So I have one, Carla. You show a matrix, a large matrix before. Yeah. This matrix is always invertible? Because in the next slide you use the inverse of A.
Yes.
So is there a guarantee that A is non-singular, right?
Yes, because of the values of this for beta between 0 and 1, the values of these the parcels will be such that this is always invertible. Yes.
Okay. Okay. So we have to move to the next speaker. Carla, please stop sharing. So Pasquale, is your time to share your slides. Okay. So let us wait a few seconds to start on time. So, Pascoal Silva is a professor in the Polytechnic Institute of Coimbra, in the ISEC, and he's going to talk about the action of electric fields to enhance drug delivery to the eye, a computational study. Pascoal. Pascoal is also a member of MOOC. I forgot, sorry.
You're muted.
Pascoal, you have to put the micro on.
Thank you, João. I will start with the end of my presentation. If this works, I'm not sure. What we can see here are two different simulations to treat the eye disease that can affect the retina. On the left, we consider intravitreal injection is an injection that is given inside the eye. On the right side is an injection that is given in the sclera. And I start with this simulation here in order to see that is a medical application, and the mathematical model are a practice of PDEs, because it's a practical of system of composed by PDEs. So this work is obtained in collaboration with Professor José Augusto Ferreira and Paulo Oliveira from CMUC, and also with the collaboration of a medical doctor that is Rufino Silva. So the outline of the presentation will be the following. I will start with an introduction where I talk about what we need to consider in order to build the mathematical model, and after I show some simulation and some conclusions. So there are a lot of diseases that can affect the posterior chamber of the eye. What we need to know if we want to study this kind of treatment is the anatomy of the eye. So here inside we have the vitreous on blue color. After the first layer on red color is the retina. After in yellow color we have the choroid, and finally the sclera. So my domain is based on this structure. And there are a lot of studies about this subject because the physical and dynamic barriers influence the drug procedure to achieve the retina. There are the main properties that we need to consider to build a mathematical model. We need to know about the physical barriers and the dynamic barriers. We need to know also that exists the aqueous humor that circulates inside the posterior chamber, in the vitreous, retina, and the choroid. About the retina, we need to know two main properties. One related with the clearance phenomena that is related with the inner blood retinal barrier, and the other is related with the pumping effect. That is a mechanism that is responsible to move some substance to the side of the choroid. We also need to know that the sclera are a layer without vessels, and that the choroid is the most vascular layer. So in the choroid, we need to consider a clearance phenomenon of drug. So there are a lot of type of treatment, as you can see in this picture. In fact, the classical devices to treat the eye disease are not efficient. So the recent years, the investigation are related with injection and implants. The idea is to install the drug or the device as close to the target tissue as possible. About implants, we published in the Siam Journal in 2018 one work related with implants, we consider biodegradable implants. As we can see in this picture, we have the Usurdex implant is an example that we consider. This implant is put inside the vitreous, and we study the difference between this type of implants and an implant that is put in contact with the sclera. Today, the focus are not implants, are about injections, and not injection given inside the vitreous. We want to explore two different spaces. One space is the suprachoroidal space, and another space that some research talk about is the subretinal space. You can see in this picture that we have the sclera on this layer, and after on green color, a very small space where it's possible to put one injection. The idea is to avoid the blood retinal barrier in order to have an efficient process to achieve the retina. Another space that can be used is represented in this picture. You can see that if the medical doctor give an injection in the very good position and precisely position, these spaces can be created to made the drug here. So what we know also is that the suprachoroidal space and the subretinal space release plus the action of electric current represent one of the last tests attempt to implement an efficient delivery process. So we also need to consider a iontophoresis process in order to help the drug to achieve better the target tissue. So our objective today is make a qualitative study about this type of injection and compare this type of injection with the intravitreal injection. We want to check the effect of the iontophoresis, and we want to give an information about the residence time and the peak concentration of this type of injection. So the mathematical model will be defined in this type of geometry. We have the vitreous, the retina, the choroid, the sclera. I put here the three positions for the injection. We will compare these three types of injection, SCS, SRC, and the intravitreal injection. And we will build our mathematical model by the following. We also need to create the electric fields, and the electric fields will be simulated by the following. We will consider a positive charge here, where is the zone where we consider the two types of injection, and on blue we will consider a negative charge. What is expected that is create electric fields that help the drug go to the optic nerve. So to solve the problem for the pressure related with the aqueous humor, we solve this type of equation. This is the Darcy Law, and we consider that the flow are not is incomprehensible. We define this last equation to compute the electric current to create the electric fields, where sigma I is the electric conductivity. In the top, we need to consider the permeability of the tissue and the viscosity of the fluid. We solve the problem in the steady state, and this kind of results is an input to solve the problem a long time for the drug concentration. So the behavior of the drug concentration is given by the following equation. We will start by the vitreous. This is a convective reaction diffusion equation, where CV represents the drug concentration in the vitreous. J, the mass flux, is composed by different terms. We have here one term that is the diffusion term. After we have these two terms related with a convective part, one related with the electric fields and another related with the normal velocity. This normal velocity VV is the velocity of the aqueous humor, and we need to consider this first term when we have an intravitreal injection. For the retina, we have a similar equation, but we have two new terms. We have this new term, gamma R, that is responsible to the clearance, the phenomenon related with the blood retinal barrier, here in the side of the vitreum, and we have also a new term on the convective term that is VP. VP is responsible to the pumping effect. So in this case, our JR is defined by these three terms, where here I have the summation of two parts. One part is the velocity of the normal velocity given by the flow, aqueous humor, and the other responsible to the pumping effect. We have defined in the choroid a similar equation. In this case, the main difference is that are not include any source term, because in this case, in this layer, we don't have a source term to simulate the injection, but we have the main term that is related with the clearance, because this layer is the most vascular layer, so is where more drug is loosed, and this drug, part of the drug are not efficient to treat the retina. At the end, we have this equation for the sclera that describe the transport of the drug inside the sclera. In this case, we don't have the convective term related with the aqueous humor. In fact, in this, we have only the electric fields and the convective term, and we have this source term to simulate the injection in the sclera. We point out that, of course, we need to couple all these equations with initial boundary and interface condition. We defined 0 in all layer for the drug concentration. For the boundary and interface conditions, we will assume that the continuity of the flux and its dependence of the mass transfer coefficients between the drug and each layer. Here I represent VR is the interface between the vitreous and the retina and the choroid, and so on, the choroid and the sclera. Finally, we define the boundary, what's happened to the boundary of the sclera, and near the hyaloid membrane, we assume that we can lose some part of the drug. To define the potential, we need a boundary condition where we consider voltage, a positive voltage in the yellow part on the geometry that I showed you before, the previous, and V0. Minus V0 in the negative part, that is the blue part. So, to solve the problem of the Darcy Law to the aqueous humor, we defined the pressure on the top of the top of the geometry, that is 2000 Pascal. That is the pressure that is measured near the ciliary body, and on the vessels that exist on the choroid, we assume the blood pressure, and we assume the continuity of the pressure to solve the problem for the aqueous humor. So, to define the source term, that allow us to simulate the injection, we will use this definition that can be appears on the sclera if the injection is given in the suprachoroidal space, or on the retina, or on the vitreous, depending on one kind of case we want to simulate. The first simulation. To do the simulation, we need to consider a lot of parameters. I only say that the diffusion that we use here are related with the dexamethasone that is used in very experiment related with eye disease. The other parameters are known and on the literature, and we will use the COMSOL multiphysics to solve the problem, and we use piecewise finite element methods. So I will start show you what we obtain for the pressure. So for the pressure, we calculate the velocity and the pressure on the steady state. On the top here, recall that we have the ciliary body and the flow go inside by this type of boundary and leave the human eye by the choroid. The values that we achieve are very similar with the values that we can find on the literature for works related only for the dynamic of this type of fluid. We solve the problem also for the electric fields. So for a voltage equal to 2, we obtain this distribution of the potential and for the current density. What we expected is to see the influence of this type of electric fields on the drug retinal for different kind of injection. So I will start by the injection that is given in the suprachoroidal space, and I show you here the drug distribution in the vitreous for 2 different times is only an example. We can see that in the vitreous, more drug concentration achieved when we have 2 hours than 10 minutes, but this is only for check the evolution on time. But what we want is the effect of the iontophoresis process. So what I will show you here is the difference between not consider the iontophoresis process after
2 minutes.
Thank you.
2 minutes.
Thank you. After we define the V equal to 2 voltage, and after I consider a voltage equal to 5, we can see that on the sclera, the drug leaves the sclera faster and go to the others layers. So this helps the drug to achieve the retina and the other layers. In this case, I'll show you the mean concentration along 2 hours when we consider the electric fields only active during 5 minutes for different voltage, and we can see that the iontophoresis process leads to higher concentration inside the retina. On blue and on red color, we have the iontophoresis active, and on green, we don't have iontophoresis process. The same for the voltage. If the voltage is lower, I go further. We can see here the subretinal injection. We can see here the injection that is given inside the vitreous, not on the retina. And at the end, we can compare what's happening for the different injections. So on purple, I have the results of the mean concentration in the retina when we consider an intravitreal injection. The other 2 closed, green and black blue, are for the suprachoroidal space, and the light blue and the red color is for the subretinal injection. We can see that higher drug concentration are achieved in this case. But if we solve the problem, not for 2 hours, but for 24 hours, the effect is different. The residence time is observed, the more residence time is observed for the intravitreal injection. So to conclude, I show you a synthesis that what kind of type of information we can do with this type of simulation. We can do an indication about the peak concentration, the residence time, the sensitivity of the injection for the inner or outer BRV, that are the retinal barriers, about the drug concentration that can achieve the retina, and for future work, we want to make more and study drugs and the binding of the drug. We want to study the drug distribution for different pathologies and so on. Thank you. Thank you.
Thank you very much, Pascual. We have 1 minute if anybody in the audience has a quick question.
Can you hear me?
Yes.
Yes.
Pascual, nice work that you have there. I wanted to ask you just some things to understand a bit more about the modeling part and that. So concerning the parameters that you said that you had these parameters from literature for the viscosity. So these parameters are there are the experimental parameters, or it was just guess by?
Yes, some of them are obtained by experimental results. Not all of them.
Not all of them.
But there are some experimental with monkey eyes and bovine eyes.
Okay. So the parameters
not human eyes.
Okay. They are quite small. You can see there the magnitudes. Okay. Concerning the dimension of your final system, how many degrees of freedom are we talking about? So you were doing the simulations for the 2D with all the coupling of all the equations. And so what was the dimension of the final linear systems that you need to solve? Well, just to have an idea, a rough estimate.
I'm not sure about that, but I have here my decision elements.
So my question, the aim of my question is to try to understand if would it be meaningful or reasonable to do a 3D simulation of the complete eye? Do you think it's
true that when we consider implants, we do the simulation in 3D. Is the fact that I start this work with 3D, but when I start using iontophoresis process, I have some problems. So I try 2D because I need to wait too much time to have some results. So I go to 2D, and now, of course, we want to go further.
Okay.
Maybe I would suggest that George and Pasquale could talk about the next talk. We have to move. Pasquale, please stop sharing.
Thank you.
Thank you very much. Now, George, you have to start sharing your slides.
I'm going to try again the full screen to see.
Okay, that's fine.
Do you have the image from my slides?
Yes. Okay, so just a few words. Jorge Tiago is the main speaker of this section. I would like to thank you very much, Jorge, for accepting this invitation. Jorge is a member of CEMAT, Center for Computational and Stochastic Mathematics, and he is a professor at Instituto Superior Técnico. His research interests are related with the cardiovascular mathematics, optimal control, problems in hemodynamics, optimal control theory, simulation, and estimation for partial differential equation. So, George, I am reading your web page. So, okay, please, you can start, please.
So thank you. I appreciate the invitation to participate in this forum for discussing applications for partial differential equations. I'm always excited about that. Thank you, Pasquale, for having me in mind. So it is true. I've been working in CMAT.
Sorry. Could you turn on your camera, please? Maybe I don't know if you have any problem.
Let me see. I think. And the microphone, is it working properly?
Yes, but now the slides, you have to share the slides. Yes, that's fine. Thank you.
That's fine. Okay. So I was saying that I've been working in the past years in CMAT in a group that is devoted to blood flow modeling, essentially. The group is led by Adélia Sequeira. She's retired right now, but she's still very active. So the fact that I have a few more minutes to talk allows me to give a more extended introduction to the subject, and I decided then to give an overview of some of the results that we have been doing there. So as a motivation for the purpose of modeling blood flow, I wanted to remind you about some facts that have to do with the cardiovascular diseases. Actually, cardiovascular diseases are the responsible for the highest death toll in Western countries. There are several of them. One is atherosclerosis. There are also aneurysms, congenital heart diseases, and some others. Atherosclerosis is actually one of the main most important, because this one is the one that is responsible for the larger number of kills. So what is atherosclerosis? You can see here in this medical image, you can see blood represented in this dark color. So we can see several vessels. This is an arterial branch. And we can see on this, the first part, that we have a kind of constant radius. And then when we have the branching, we will see that we have a narrowing here. So the radius, the space available for the blood to flow will decrease. Atherosclerosis is a disease that is a type of inflammatory disease which leads to a deformation of the arterial wall itself, and that will lead to this narrowing. So this can happen in the coronary arteries, which are the ones that are responsible by bringing nutrients to our heart muscle. But it can also happens in the carotid artery. So there are several problems, but one of them is that you can imagine in the heart muscle, if blood starts flowing in sufficient quantities, then the muscle will not receive the nutrients, and the person will end up having a heart attack. Otherwise, if you have a plaque like this in one of the arteries that are supplying our brain, there might be a rupture of the plaque, and then some of the debris that will come from here will follow the stream and will end up blocking of our brain, and we will have a vascular accident, a brain vascular accident. So those two are known as the major causes of death. Another one, as I mentioned before, is aneurysms. So aneurysms, the aneurysm is a process that is, in a sense, the inverse, because the artery will not get more narrow, but instead it would get larger. So what happens here is that due to several reasons, the artery wall will start deforming. There will be a rearrangement of the artery wall cells. It's a type of disease that will lead to a deformation and increase due to the action of the fluid itself. So once we have an aneurysm, they can have different shapes. We have the risk of rupture. So the aneurysm can go into rupture, and then blood goes out from this region to the brain mass, and you can imagine all the consequences. So this is not as common as a cause of death as atherosclerosis, but still one on every 20 person will have an aneurysm, and then some of them will have a rupture of the aneurysm. So another type of cardiovascular diseases is the congenital heart diseases. I'm thinking in particular in one of them, that is the bicuspid aortic valves. So this is a representation of an aorta. Here we have 3 leaflets that every time that the heart pumps, they will open, the 3 leaflets will open, and then blood flows through the circular system. So it happens for some people, some they already, so they will born with this pathology, that instead of having the 3 leaflets, they will have, let's say, just 2, because 2 of them are merged together, or they actually were born with just 2 of them. So the blood will not flow in the same manner, and with time, some dilations of the aorta may occur. We have here 3 representations, illustrations of different types of dilation. So this is one type of congenital heart disease, which may have serious consequences, because people who have this type of pathologies, they may live not much further than 30 years old or something like that. So doctors are very concerned about this type of pathologies. And what does this have to do with mathematics? Well, the thing is that right now we have computer power, and we have knowledge about mathematical modeling and numerical techniques to aim at having computer simulations that can be considered patient-specific, from which we can have extra measurements that will help guiding doctors in their clinical practice, namely for their diagnosis purposes. This is something that myself, in my experience, I have found that doctors, they come to us asking us for these techniques, to use these techniques with their data, so that they can have extra insights of what's going on. So all this is an ongoing research, but it's quite promising. So when we are talking about blood flow modeling in the circulatory system, well, we need to set our assumptions. Actually, the cardiovascular system is huge. It's composed by a closed loop system with tens of millions of vessels. We have the arterial, the venous system. It's impossible to model as a whole, but we can do some things. So there are models right now that try to model the closed loop system, including not millions but hundreds of vessels. These are simplified models where the blood velocity and pressure are taken as average values, representing one of the vessels that are being modeled. If however we need more detail, let's say a 3D detail, if we need to measure stresses, if we need to measure changes in local changes in pressure or vorticity, then we need 3D models. These 3D models, they are quite heavy, but they make sense if we are looking at some larger vessels, such as the aorta or some of the main arteries that are irrigating our brain. When we are under this assumption that we are dealing with large enough vessels, so we can actually look at blood and think on it as if it was a fluid with certain properties. So for this type of vessels, we are talking about radios that can range millimeters, sometimes even 1 centimeter if we are talking about the aorta. So when we look at the main components of blood, we are talking about essentially water, the plasma, but this water is transporting particles, cells, and the larger number of cells are the red blood cells. They are responsible for 45% of blood volume, and they are quite small when compared to diameters of millimeters or even 1 centimeter. So we can, let's say, neglect the movement, the displacement of these blood cells on its own, and think on blood as a fluid. There are other blood cells that are larger, like white blood cells, but they are much more sparse. So it is the red blood cell that will define the rheology of blood. Actually, blood in general is considered a non-Newtonian fluid because when we have a small change in gradients of the velocities of the flux, these red blood cells, they tend to aggregate, and therefore the viscosity of the fluid will increase. While if we have big changes on these gradients, then we'll have lower viscosity. So this change of viscosity must be captured by the model that describes our fluid, which is blood in this case. We also have the artery wall, which has several layers. We will be talking about this a bit later. Let me first address the question of the fluid. So when we are talking about modeling blood as a fluid, we need to think about some physical principles. We have the balance of linear momentum, the balance of mass, we have angular momentum, and we have the energy equations. So it is quite acceptable to consider the temperature to be constant, except for certain purposes. So we know that blood essentially will be at 37 degrees Celsius, and also the density can be considered constant. Under these assumptions, the energy equations will become redundant, and we are left with linear momentum and mass conservation and angular momentum. When we talk about the linear momentum, you all know the basic, the most simple version of linear momentum equation. Here we need to think to describe blood through its velocity. We will not follow each of the blood particles along its displacements. We are going to fix one part of the domain, and we are going to see what happens to blood as it passes through this part of the domain. So how is the velocity changing? So our main variable is the velocity of the fluid, not the displacement, as it will be in this classical version of linear momentum equation. So we will need to have locally the linear momentum locally, before being integrated, will be represented by the density times the material derivative of this velocity. This is what will give us the acceleration that we have here. And then we will have forces that have to do with the contacts of each small element of fluid on each other, plus some external forces like gravity. So when we look at this material derivative of the velocity, and if we want to extend it to derivatives, let's say usual derivatives, we will need to consider the time derivative of the U itself plus the convective term. And then if we want to be more explicit concerning the forces, so we need to define how are these contact and surfaces forces. So we need to define locally what is the divergence of the Cauchy stress tensor. So it is this Cauchy stress tensor that is going to define the properties of the fluid, the way it reacts under stresses, under variation of stresses in this case. So what is this this tensor? What should be the tensor when we are talking about blood flow? So one of the most accepted hypotheses is to consider blood flow as a generalized Newtonian fluid, which means that the tensor will be split into two parts. One part that is the viscous part, and another part where we have the orthogonal stresses, where a new variable appears. This is what we are going to call the pressure. Also, viscosity, here represented by mu, will in general depend on this measure of the gradients of the velocity. Here we have d of u represents the strain rate tensor. So this is a measure of that has to do with the gradients of the velocity. This is called the shear rate. So mu depends on the shear rate itself. So we have a new variable, and we have in general this dependence that can be non-linear or linear if we assume that the viscosity will be constant. Also, another thing that I would like to say is that we also have the conservation of linear momentum. The conservation of linear momentum in this case will bring us to the conclusion that this Cauchy stress tensor must be a symmetric tensor, and the fact that we define it in this way already have this information implicit, so we don't need to consider anymore the equation. We do need to consider the mass conservation, which typically will be written in a compact form like this, but locally, for our case, it will have this form. Because we have a density that is constant, we'll end up having this equation, as already Pascual mentioned in the previous talk. So we have here essentially two equations. For the wall modeling, the main equation is again the linear momentum. Actually, in this case, we do want to follow each element of the material, so we are no longer looking at the velocity, but at the displacement itself. So we have the second time derivative of eta, which is the displacement here, and we have a force that once again will be given by the divergence of a certain tensor. So this tensor, because we can see that this tensor is not a symmetric tensor, it can be written in terms of a symmetric tensor, and the way we define this symmetric tensor will describe the properties of the wall. So here there is a huge field of research. That's not my field of research, but I wanted to tell you one thing. So we can consider the artery wall as a kind of homogeneous structure media with average properties, or we can consider it as a multi-layer domain. We can consider it as an hyperelastic material that depends on our aim. What are we pretending? What are we aiming at in terms of modeling? In general, for the purposes that we have been using, we define this symmetric tensor through the Sanvena model, which is an elastic model. This is a possibility. As I said, there are others. So at the end, we will have let's say a system of equations for blood itself. So we have the conservation of linear momentum, the mass conservation. Then we need to fix boundary conditions. So we will say that the velocity of the fluid at the wall is 0. This means that let's say the molecules of the nearest layers of blood, when they encounter the interface with the wall, they will stick to the wall. If the wall is moving, then the velocity will be the velocity of this movement. If the wall is fixed, the velocity will be 0. Okay, so for the moment we would assume that the velocity of the wall will be 0, then the velocity will be 0. Otherwise, we need to put something here. I will mention that. So then we need to put some influx at this artificial boundary. We can call it a V. And then we can say that we have some stress acting here. In some cases, we will assume that no stress is being applied if we are not interested in what happens in this area. In this will be this case here, but in general, there will be some function here describing the stress vector being applied on this area. So this is a setting that is quite common in when modeling blood flow. So, but I was saying that we are talking about the couplets model, and so in the couplet model, we will have a deformation of this domain along with time. If this deformation has a certain velocity, then our linear momentum term here will depend on this velocity, on this deformation velocity. So if we put everything together, besides the equations for the fluids, we will have an equation for the structure. And you see at the boundary that we call the wall, because is the one that is physically that is a physical boundary and that represents the interface between fluid and the structure, then the velocity, instead of 0, if we have a movement, it will be the velocity of that movement. Also, we will need to have at that same interface, at that same wall, we'll need to have some continuity of the stresses, of the stress vectors that are acting on that same interface. Okay, once again, we can have some non-zero boundary conditions on what we consider the gamma out. Okay, so this is a very complex system. So in its full generality, it has not been mathematically analyzed, let's say. It has been mathematically analyzed for certain versions of boundary conditions. Also, in fact, even the Navier-Stokes equations itself, they have some open problems, even before coupling it with the fluid structure interaction. In terms of numerical methods, both cases, the Navier-Stokes equations or the couplet system have been quite studied. There are some energy inequalities that can be derived, and so finite element methods have been used to approximate the solutions of this couplet system. I'm not going to go into details about this. I wanted, however, to illustrate some applications of this model that we did by requests of medical doctors. I wanted to do this before going a bit further, according to time. So the first application that I wanted to mention, so it was something that came up from contacts from cardiologists from Santa Marta Hospital in Lisbon. Silvia Aguiar Rosa, Dr. Silvia Aguiar Rosa, she was interested in having more detailed knowledge in some aortas with that problem, that pathology that I mentioned at the beginning, the bicuspid aortic valve. So instead of 3 valves, people had only 2 of them, with different shapes. And she wanted to know how this type of methodology could give further insight, understanding what happens with the fluid in these cases. So. Diana Oliveira, she was a researcher at CIMAT. She is now finishing her PhD in Birmingham. She was enrolled with us in this task. So from the medical images that Silvia gave us, we managed to build several computational representations of it. These are just 3 examples. Then Diana did a very exhaustive work to try to represent exactly how the bicuspid valves were. So these are based on patients on medical images. So these valves become fixed, although they have some movement here. It was considered as fixed. Then we had also average velocities along time for each one of the patients, and we were able to apply the ILE approach, numerical approach based on finite element methods to solve the coupled model that I've showed to you before. So we had extensions here where we input these average velocities. Then these will be adapted to this shape of the bicuspid aortic valves, and then at the outflow we couple it with the type of simplification of a reduced model that actually I got to know through Alexandra Moura. It was her sequence of her PhD. Her PhD thesis, which are a type of boundary conditions where we imposed the traction at these boundaries in such a way that it will receive information about the flow rates, and then it will avoid spurious reflections. It does not have information about the remaining system, but at least does not has a certain type of oscillations that will appear if we just fixed a certain traction or zero traction or so. Okay, so this was an example of the results that we gave. We have several conclusions from here, but I want to go fast. From the same hospital, we also analyzed other aortas for, in this case, from children. So it was from pediatric cardiologist Sergio Laranjo who contacted us. I wanted to show you here a simulation where we can see one of these stresses that I was mentioning before that they cannot get in any other way. So what we are seeing here is what is called the wall shear stress. The wall shear stress is a projection of the stress vector that the fluids. So when the fluid will act on the interface, there will be a stress vector resulting from this fluid action. We have a tangential projection of it, and this tangential projection we can have a magnitude, and what we are seeing here is the magnitude of this projection, and we can see that it will be. So we see along with the pulsatile nature of blood, we will have a non-homogeneous distribution of these magnitudes. And so this is the type of indicators that they like to understand, because they like to see, according to the shape of the aorta, where are the areas where these tensions are higher and where are the areas where they are lower, etc. So these are extended measurements that can help in diagnosis purposes and decision making. So another example. Let me just, before going to the next example, I would like to ask the chairman, because I am in full screen. I don't have a time. What time do I have left?
About 10, 12 minutes to finish.
Okay. Thank you. Good. That's perfect. So another example that I wanted to show you. This one resulted from a collaboration with the Coimbra University Hospital from neurosurgeon Ricardo Pereira. It has to do with aneurysms, the other pathology that I mentioned also before. So we had different purposes here. I choose to bring a couple of images that can illustrate, let's say, the possibilities. Again, the idea, so essentially the idea here is to try to have a way to predict, based on computational simulations, to predict, if possible, if one aneurysm can go into rupture, if the risk of going into rupture is higher or not. I must tell you that the results were not that concluding. We would need a larger number of cases to draw some conclusions. So the method seems a proper method, but we need massive studies to draw some conclusions on that. Still, to illustrate the procedure, let me show them. So we have the medical images like we have here on the left side. From those ones, we can construct the computational domains. We need to go through a procedure of filtering and smoothing, etc. And then we compute the meshes. These meshes, because we only have part of the area that we are interested in, so we cannot reproduce everything. So if we have some average velocities to consider as inflow, one way to deal with this lack of information is to extend the vessels as if it was a pipe, so that we can put these average velocities at the entrance of this pipe, and then along with the pipe, this bulk flow will adapt to the boundary conditions. If we are far enough, then it is expected that when we arrive here, at least the boundary conditions had some effect on it. So this is a way to overcome this lack of information that we have from the rest of the system. Okay, we did the numerical simulations using it was Phoenix, so it's a Python-based pack of finite elements methods libraries. So with P2, P1 elements. So here you can see streamlines. The streamlines are essentially integrals of velocity vectors. So we define a certain number of points and we start integrating from there, and you can have this idea about what will be these path lines in a way. Here we have, in some sections, the magnitudes of the velocity vectors. Here we have the vectors itself, and then we can also have vorticity. So you see, for instance, right now, doctors may have some information about magnitudes. They may have some information about velocity vectors with a lot of noise and quite sparse. Vorticity they cannot have, and they cannot have the other type of informations that I mentioned to you before, which like the wall shear stress. And this brings me to the one other application that we tried. So here we can see for one of these aneurysms, we can see pressure. So the pressure resulting from the fluid action in the interface, we can see the wall shear stress divergence and the wall shear stress itself. What are the purpose of having here these two quantities? Well, the wall shear stress is the typical quantity of interest, but here we are seeing a wall shear stress as a vector that is aligned with the velocity at the wall, while the divergence of the wall shear stress is perpendicular is aligned with the velocity that is perpendicular to the wall. Why are we interested in this? Let me go back just a bit. You see, here when we have the streamlines and we want to understand what happens with these flow structures, you see that close to the wall, we never have much information. Why? At the wall, we are fixing the velocity to be either equal to the displacement of the wall or either zero. Actually, here we assumed the artery wall. We neglect the movements of the artery wall. That's what I was going to say. We neglect these movements, so we don't have elasticity here. So we just have fluid. So here the velocity itself is zero at the boundary, at the wall. So if we are going to do an integration, we cannot integrate we will not. From this zero, we will not have the information that we would like to have. So by considering these quantities that we compute at the wall itself, then we can infer information about the velocity at the wall, very close to the wall. It means that otherwise we will not be able to. So, and this will allow us to establish what happens in the nearest regions close to the wall to what happens inside. So inside we already had this information, but now we can make the link between both. And in terms of when we look at this, when we look at this, let's say the critical points of these wall shear stress vectors, we then could find some connections between the ones that went into rupture and the ones that were not. But again, none of those were conclusive, and further studies would be needed. Okay. I have some free time and some remaining time, and I want to introduce another topic. I had worked before on this, then I stopped for a while, and now because I have a project on this topic, I'm coming back to it again. So, as I mentioned to you before, we are interested in analyzing the fluid in one particular district, and then we are neglecting, in a way, what's happening before, upstream and downstream these districts here. So we will need to overcome this lack of information. We may have some information about velocity vectors sparsely. We may have some information about velocity magnitudes or average velocity. This is something that we can get in kind of in an easy way, but not for all the domains and not where we want. So we may have something here on this area, but then we will not have on this one, or we don't have here. So how to find, for instance, if we have information somewhere on this area, how to find what are the boundary conditions that we should put here. So there are different ways of thinking about this. One is the control approach, which is the one that's by education, let's say, I'm interested in. So what are we doing when we are talking about the control approach? So we have our system. Let's assume that we are neglecting the artery walls displacement right now, just fluid. So we have the fluid equations here. We have that on our boundary representing the artery wall, the fluid does not move, it's just attached to it. And then we might know some pressure values or some other information in some of the boundaries, but we do not know some other information. So we want to find what boundary conditions should we consider where we don't have information in such a way that, for instance, if we have velocity measurements in some part of the domain, then we can match these kind of least square terms. So we can minimize these least square terms here. So typically we will have only some sparse information. So we would need to interpolate or use some techniques to extend it to the whole domain. Or we will also have some information in some time steps. So we need to see if we really can use this integral here, or we can just, or if we do some interpolation, or if we just use a sum, a finite sum. But this will be like the general goal that we would like. So find as a control variable a boundary condition, and then as a functional to minimize, a function that will have this fit to minimize here. Of course, with a bit of knowledge, we know that we must have also some regularization terms that have to do with the control variable itself. So this idea did not come from me or someone in my group. It came from Alessandro Veneziani and people, his collaborators. In 2010, they published a paper where they were addressing this type of issues for the stationary case with pressure control. But we did some work concerning the velocity control itself. I think I still have a couple of minutes to give you an overview here of some.
I would say 2 minutes to finish, please.
Okay. I have here more slides. Don't worry, because this was for discussion purposes. So I want to give you here a quick overview about. So you see, when we first addressed this issue, we found out that for the non-Newtonian case, there were only some results in the stationary case with the Neumann boundary control and distributed, so none of them would work. Even for the Newtonian case, the same happens, except for one paper here from Hanakar and Fursikov. They did some interesting things for mixed boundary conditions type. We then addressed the problem in the stationary case, and we published some existing results for the case that we were addressing there in the stationary case. And later on, this was extended with a more complete analysis by Andrea Manzoni and Quarteroni and Salsa. Actually, the time-dependent version has been from let's say from a computational perspective, has been more engineering perspective, let's say, has been tested, and it seems to give good works. I have here some references from people doing this, but there is no mathematical foundation for it. So we have well, I'm the PI of the project, so with people from IST, also from University of Lisbon, the Faculty of Medicine, and the University of Bristol, we got an FCT project with the aim precisely of addressing this problem. So we would like to do the mathematical analysis and the numerical analysis for the control problem with the time-dependent in the time-dependent case. Of course, by doing that, we can also then evaluate or access the possibility of using other types of boundary conditions, or using other type of control approach, like a feedback control approach. And of course, in the limits, one might try to use to do the analysis with the fluid structure interaction. That will be much harder. There are some works in more simple versions. We have nevertheless 2 postdocs. We launched, and it should appear quite soon, the call for 2 postdocs aiming to work on this. One more, let's say, more for the computational purposes, and another one for more theoretical aspects, and also some young researchers, dedicated scholarships, either at the master level or just having completed. I would like to advertise and to spread the word also on this. Okay, I will let for the discussion some some cases illustrating this, and let me instead show here some references, and up here with some references where you can let me see. I think it's here precisely. No, it's here. These are some references of work that we have done on this. I recall that, so we did some work on this and then we stopped. I was devoted to these other works that I've presented before, but now we want to go from here, especially for the time dependence. But I invite you to take a look at these references if you want to see also some examples, some computational examples. So I think I have no further time. And I should wait for some questions.
I think we should finish, because it's the we are a bit behind the schedule, but I think we should finish.
Okay.
So I would like to thank Jorge, Tiago, and also the other speakers, Hugo, Carla, and Pasquale. Thank you very much for this. It was a very nice session. So maybe Pasquale wants to say a few words.